Whether my screen is visible?
Yes, sir.
So last class we discussed many things, and we particularly said that why this support vector machine, in short people call it SVM, is so important as compared to MLP and a radial basis function network. So and the last class, after the basic motivation behind the SVM, that is basically it tries to the main the significance of SVM is something like it's position the decision boundary in such a way that decision boundary is at a maximal spacing from the positive and negative example, means from the either side, which is not the case using either RBFN or using MLP. So after with this definition, we didn't do anything about SVM. Then we delve into the required mathematics required for this, and we did a lot of concepts we went through. And now we'll move to this the rest of the concept left in this SVM chapter. So another thing which I'm going to talk about, this we already discussed, is talking about a discriminant function. So basically, one way to represent a classifier is by using discriminant function. Means there should be something which is discriminating the points from positive example to negative example. So we use something called discriminant function. So we see that it works for both binary and multi-class classifiers. So here we will be discussing about the binary classification only, to either positive or negative, but it works for the multi-class classification as well. The idea is simple, that for every class I, let's say those classes may be 0, 1, 2, 3, K. So don't consider the index, just the label of the different classes. And we define a function gix to R. So this X is basically the data point which you're talking about, and it's maps to R. So when the decision on the input point should be made, choose the class with the highest value of G. Highest value of G means overall. So accordingly, it is it gives this the which particular class it belongs to. So we'll see this particular concept here. And now formally I'm going to start this SVM. What is going to we are going to find is optimal hyperplane for linearly separable patterns. So we'll study this SVM in two phases. For the first one, we'll try to find optimal hyperplane for the case for the data points which are linearly separable. In the other segment, we'll try to understand how do I extend this concept so that the data points which are non-linearly separable, how do I find optimal hyperplane for that in the SVM jargon. And here I just wanted to share something because we are showing it here. So okay, just let me use this. One board will be used. So sometime you may come across this kind of notation. So don't, I think I have already told, but still, like training example is mentioned here. Normally it is written something like xi di and I is varying from 1 to m, whatever. There may be also a possibility that you might see something like this. X I superscript di superscript I equal to 1 to m. So this is not a power as such. It's saying that it's ith training example and ith desired value. That's all. So don't get confused with this power. So it is not anything to do with the square, etc. Means ith example. Either we use this one, and some books they use this kind of notation. So it may vary. So you should know the context should be clear to you. Means in what context you are using it. Okay. Now let me go to this and we'll see about this. So for the simple of sake of simplicity, we are considering, of course, a training example, something like this. And we are assuming that the desired labels or the values are +1 and -1. So just a desired label for the sake of simplicity. This you could have taken anything. So we are saying that two classes are there. Now equation for decision surface in the form of a hyperplane that does the separation. This you know that basically there's a decision. So this is some weight vector which we don't know. X plus b equal to 0. B is for the bias. Now we may write this. This is whenever we find this decision surface or the decision boundary, it is always like this. And I have already told you, because from the decision boundary, it is always weight vectors always point in the perpendicular to the decision. And that's why actually the WTX equal to 0, which is nothing but the normality. And because bias is also considered, so it is written like this. Now, this particular decision boundary can be written in this particular fashion. Say that WTXI plus B means for the ith example which I'm considering, if that value, this value comes out to be greater than or equal to 0, then this value is belongs to positive class. And if it is less than 0, negative class. But there is no standard hard and fast rule. This is only the notation we are only adopting. If you want this to be -1, this will be +1, even you can do that as well. There's no problem with this. Okay. Now, so here for this one, for a given weight vector W and bias B, the separation between the hyperplane defined as per this equation and the closest data point is called a margin of separation. We call it a margin of separation between the two. So this I already explained during the last class. What do you mean by margin of separation? And the goal of SVM is to find hyperplane for which rho is maximized. The margin of separation is maximized between the two sides. Okay, so that is the overall goal. So how do we go about this? So under this condition, the decision surface is referred to as a optimal hyperplane. If you are able to find rho which is maximized, so such kind of decision boundary, whatever we get it, that is called optimal hyperplane. Now we'll see that how we are going to formalize this for the linearly separable case. So linearly separable case is something like this. Simply, you can consider this as a positive or this as a negative or vice versa. And we are looking for certain points, and this distance overall, this is the basically margin of separation between the two boundaries. So this is something for the negative class, this is for the positive class. And remember the data point which lies on this line, or this line, either side, is called support vectors. Why we call support vectors, that you'll come to know soon. Now, but before this, to study this geometry, I have to do something. Also, so we'll see that this geometry is quite involved when we do the analysis. So I'll explain this. But before that, assume that W sub O and B sub O denote the optimum values of weight vector and bias. Means suppose that you have found them. Now the optimal hyperplane representing multidimensional linear decision surface in the input is defined by this one. Only thing, instead of W, we are writing W0, thinking that let's say this is optimal list, this is going to be optimal value. If this is the case, so we have something here. So the discriminant function which I was talking about is something like is a function which is going to tell you that what is the label for it. If you remember that I was talking about in mathematical regression, I note that if the value of gx is basically x to r, so based on that we'll decide the class. So basically based on this only we are going to decide in this. Why? Because here if you see that if this entire part I'm taking is gxi, and if it's greater than 0, so I say that it belongs to class 1. And if it is less than 0, then we say class minus. So this entire part can be called as a discriminant function. Now there is no uniform or universal definition for this discriminant function. From the problem to problem, its definition varies, but you should know what does it mean. Okay. So once we have this, so basically it gives an algebraic measure of the distance from x to the optimal hyperplane. And this something has come, but from where it has come? In Simon Hagen, he directly writes this without explanation from where it comes. So let's go to the board and try to understand. Means how this has been how this can be written as, and further simplification how to do this. So be very careful about this, because this is something is not given in the book and you should know it. So here we have draw just mind my free and drawing. It's not that good. And let's say this is my decision boundary, which I'm calling as in my optimal hyperplane. Just assume it. When this is there, so remember that the direction of weight space will be always 90 degree to this. So let me see if I'm taking from the horizon. So basically it is indicating you this kind of weight space vector. So this angle is 90, okay, and of course this will be 90 either side. Now let me go find another data point. Let me say it's something randomly. Let me call it some data point x1. Let's say simple, just to, and then from the origin I have to extend this line to say that what all this distances is etc. But okay, let me say this particular point. Now this angle theta, and I want to find the projection of this point x on this line, that is a weight vector. So this one, uh, you get it from this resolution of vectors. You remember, we can get it across. But before that, we know that for this particular thing, if optimal x plus b naught is there, so a decision boundary, this value comes out to be 0. It means w naught t x equal to minus b. Okay, so this will now distance from the origin to the hyperplane means from here to here. What is the distance would be? So let me mark this distance and call it as some d, some distance d. If I want to find it out, don't you think it is the same thing when I resolve it on this one, project this particular point on this one, because somehow I can find this angle is given, so I can project it on. So this will give me this particular distance. So remember the resolution of vectors in physics which you have studied. So it is nothing but d is x, whatever the Euclidean norm of course, from cos of theta, and cos of theta means what? Theta, what is the angle between the w and the x1? So I should write this theta, which I can write cos of w0 vector, I can say, or x1, only this much, right? Is that okay? Now if that is the case, but if you want to know only this cos theta, but we know that, so we can write that between this and this vector. So if you remember, I don't know whether you really remember or not. Let's say there is a theta, you call this as a vector A, this is you call vector B, and cosine of this angle between, normally we do, how we do this? We write A dot B and we say A, B and cos of theta, or we say cos of theta equal to inner product of A and B, and this magnitude in denominator, right? So from this concept, if I want to find this cos of angle between this one, so I can write it from this particular point, cos of W0 x1 equal to AB. AB means I can write uh, x is a vector, W is a vector, so I can write x1t WO or W0 t x1. I could have written that way without any problem. X1 magnitude, W0 magnitude. In school we used to write this arrows, so I have taken from that particular point. But it is a very large vector and all, we don't use arrow anymore. Now, having said this, finding cos W0 x1, we can substitute here. Now, D could be x1 and then this entire part. x1t wo or wot x1, anyway is this inner product only, and then here x1 magnitude wo magnitude. So this will go, and so this comes out to be x1t w0 over w, right? But which always can be written as t x1 over w. Now we know that how much is this one, and this value which we have written is nothing but minus b naught, bo. So I can write it now that d equal to minus bo wo, and of course, sorry, this magnitude has to be written. Now just see it and let me know whether we are on the same page till now. Hello? Are we on the same page till now? Whether you understood everything what I am doing now? Hello? Hello? Okay. So I assume that all is well and you are following this. And why I'm doing it, right? Why I'm doing it, I was talking about this kind of thing that, okay, when you find optimal hyperplane or whatever, so you wanted to go for this kind of decision boundary and you wanted to say, so we wanted to know how do I find this row, all the story. So that we'll see. Now we'll take an arbitrary point to the hyperplane and we'll say that this particular point is, let's say, x, some arbitrary point x. So it goes not x1, just x, and we have projected, extended it, extrapolated here. Now if that is the case, I can drop a perpendicular on this line, right? And I can draw a something like this, right? And let me call this particular distance, let me call r. So we'll consider two cases. Assuming that this point lies beyond the hyperplane, means the positive side, then what will happen? And if it lies inside this here, what will happen? So first of all, let's take this case. When I consider this one, so this entire part, you can imagine that from this one x1, when projecting here, this will give a distance of d plus r. Okay, so d plus r. So case 1. So we'll say that case 1. What is the case 1? Case 1 is when point x is in the positive area, right? That is above the hyperplane. Above the hyperplane, this hyperplane above. Sorry. Now you have this d plus r. By d plus r, I want this distance from the origin here to here. What is going to happen? If I'm able to find it, subtracting this will give me this. So d we have already found. So this will be nothing but, as again we are applying the resolution factor, we are finding this particular component. So this is cos of w naught x, right? And so we want to find r. So r will be nothing but again cos of w x minus d. D we have already found it. So this anyway is there x. And for cos we know that we can find it now. So that will be w naught t x. And in denominator it is nothing but w o n x, right? Minus d. Minus d is nothing but minus b o. So this x will go. We have WOT x minus, and then this is denominator WO, this is WO. So denominator is WO, this minus and minus becomes plus O, and this is your WO, right? So this is R when it is lying on the positive side. Now let's see what happens when case 2, when R, this particular data point lies inside. Suppose same distance almost here inside. What happens to that? So in that case, if I want to find this R, means how much inside this R, so I can find this R, it means D minus that particular projection. Imagine that it was somewhere here. So how much? So overall D you already found, and the projection if you subtract, you will get the inside one R. So here I can do this. So R equal to P minus X and cos of WO X. We'll substitute all those things here. Now here we had this VO, which we already found, and minus, and this WOTX and X. This will go. We can write this minus BO minus WOTX. Now, which I can always write as a minus completely, WOTX plus BO. Right? So this is the R. So basically what you are trying to do this, you are finding this distance. From positive side it is R distance, from the negative side it is R distance, and overall distance what is called rho, that is a margin. And then now we are calling this R, and you have already seen that discrimination's sake we have said that g of x is nothing but WOT x plus b. So I can see now for R it is nothing but gx over. So based on this, either it's a positive or negative. Now we'll see this how we go about it. So once we have this, then this particular part which we have already done here R, we have to find this rho. Rho is nothing but 2R. 2R. So 2R here, when actually the value of this is always 1, plus 1 or minus 1 we are saying as a margin. Margin we are taking as a plus 1 or minus 1. And why we are calling as a plus 1 or minus 1? Remember that we said that two conditions. W naught T, let's say Xi plus BO. If it is greater than or equal to 0, it means the desired value for this is plus 1. And W naught T for the ith example Xi plus BO, if it is less than 0, then Di equal to minus 1. So that's why instead of Gx, and we said that Gx is nothing but this value only. So it could be either 1 or minus 1. So either way, if it is plus 1, so no problem. It is 1 over WO. When it is minus 1, so basically it was minus coming, so minus plus plus. So R remains Gx by W. So basically it comes out to be, rho comes out to be 2 over WO, right? Is there any query by somebody? Is there any query by somebody? Any
So
con
actually the quiz link is up. Can we give that?
which one?
Quiz link is up.
Please go ahead, go ahead. Shall we resume now?
Yes, sir.
Okay. So this we have seen, and I was saying that of this particular part, that is rho equal to 2 by W, which you have seen. And you know that rho is basically is nothing but this one. That if this is positive class, this is negative, etc. And rho is this distance, overall rho. Now our objective is to maximize this rho. Now in order to maximize this rho, how will you maximize this rho? What will you do? What will you do so that it can be maximized? What is variable here? Anybody? So we'll go for this. So this we have already, I have shown you when origin B, etc. what will happen. So this geometry I have explained. So this is, we have to maximize this. In order to maximize, what we have to do, that we have to minimize this denominator so that overall things is maximized. And denominator, what is that? That is the weight space, the magnitude of the weight. So we'll see that, and here the definition of the support vector and margin separation is given once again. So optimal hyperplane is supposed to maximize the margin of separation rho, and this, with that requirement, we can write the condition W and this one meet something like this, which we already done it. So instead of writing equal to 0, we are writing something like this. So suppose support vectors are those vectors where equality holds, means and exactly they meet at the margin at +1 and -1, means here. If this is +1 or -1, whatever is that, that is exactly they meet. And those points are called support vectors, which are denoted by x of s here, x of s, right? So Wt x of s equal to B0, either it can be +1 or -1. So R, which I have written already, that I have already defined this could be 1 by W0, this one, and minus this one. So this already we have seen that there is a margin of separation between the two classes is rho equal to 2 by W0. And to maximize this one, we have to minimize this Euclidean norm of the weight vector. That is obvious. Now, then we have to rewrite this. The goal is to develop a computationally efficient procedure for using the training sample T to find the optimal hyperplane, subject to the constraint that this. Now, any idea from where this constraint came all of a sudden? So this is nothing but, if you remember that, here we have, so let me take you to the board again. These two conditions are there now, which we rewrite something like this, because so here we are writing these two conditions. Either this one +1, and of course when di equal to +1. Now if I want, I can combine these two constraints into one by writing di W0 t xi plus b0. So whenever di equal to +1, it will become just plus b0 +1, no issue. But when di is -1, so this will become basically inequality will change. Minus, when you multiply with the minus, this inequality will change. W0 t xi plus b0 less than -1. This will be there. For that sake only, we are saying this, that We want to maximize this row subjected to this particular condition. Now simply we cannot maximize. Maximizing means minimizing the denominator part. So we have to rewrite as a problem statement. So we say that given the training sample so and so, find the optimal values of the weight vector W and bias B such that they satisfy the constraint, this one. And therefore, how many constraints are there? N number of constraints, that is a n number of data points. And the weight vector that minimizes the cost function. Actually, we are in denominator, it was this one. Euclidean norm was there. And remember that Euclidean norm that is there. So we can, that one directly is not differentiable. So we do something like WTW, and 1 by 2 is the scaling factor. Just for the sake of convenience, we do, because when you differentiate it, it is twice of this one. So this optimization problem is called primal problem. So remember that I was discussing about something called primal problem and dual problem. So this is one is particularly this primal problem, and it is characterized by this one. It's basically a function. Phi of W is a convex function of W. How do you know that it is convex or not? How do you know it's a convex? Hello? Hello? Okay. So this convex, if you remember that we said that we find the Hessian, or you can say a double derivative of this. And if that value comes out to be positive, then this particular function is called convex. And of course, if you do this, you'll find that it is a convex and greater than 0, that positive value. That's why it is convex. And we have seen it also the last class. Now constraints are linear. This is complete WTX. So constraints are linear in W. So this we can solve this constraint optimization problem using method of Lagrange multiplier. See here, basically we want to minimize this subjected to this constraint. So if that is the case, we have no option but to apply the Lagrange multiplier to transform this constraint satisfaction problem, constraint optimization problem, into an unconstrained optimization problem. Lagrange multiplier, if you remember that, what we do, we can write Lagrange multiplier. So J or any function if you feel like. So WB is already there. And because there is only one set of constraints, so even though there are n, so I can use one set of Lagrange multiplier alpha or beta, only one I can use. But suppose there was another set of constraints, so another set of Lagrange multiplier, I should have used it. So this is my objective function, and from that one we are using this value. So this value comes out to be, and why it is comes something like this is that because here if you see, constant should not be greater than equal to 0. It first of all it has to be rewritten so that this inequality is proper. That should be less than equal to. Less than equal to means you have to multiply by this minus 1, so this will change, and here this will become minus 1, and this will come this side. So, and based on that particular problem, so what we did this, so this minus will come to that particular factor. Alpha this constraint minus 1. So this is our Lagrange function. Once your Lagrange function is available, so this becomes a ordinary unconstrained optimization problem. So what we do here is that we apply this simple procedure of MLE. We apply, that is maximum likelihood and this one estimate kind of stuff. We take the gradient equal to 0. So basically there are three variables, W, B, and alpha. So we'll have to differentiate with respect to each of them. Okay. So please let me know if it is all clear. Believe me, when you start reading your own and these things are not clear now, it will be create a hell lot of problem for you. Very difficult to understand that way. But if you don't have any doubt, it's good. So what we do, we go for this differentiate with respect to D, J, W, and B. That's and we have to equate to 0. So we'll see that how do we go about it. And that is straightforward, should not be a problem. We've got a smart guy now. We can apply this calculus results and we get this. So the first one, when I differentiate with respect to W, so what will happen there? Here is that particular, this particular part. W equal to y equal to 1, because only this part will have this one. Here it is becomes 2w by 2, so 2 will cancel, and only w, and this is because w is there, so remember that we are differentiating with respect to this one, so we will get only uh, this alpha I di and xi, rest will be 0. When we equate to 0 everything, so we'll get something like this: w equal to I equal to alpha I di xi. This is the thing when you apply this kind of optimality condition. When you apply second optimality condition, see what will happen, because it's with respect to b, this plays no role, it is as good as 0, only this part is there. So here it is alpha times di, and when I differentiate with respect to b, this entire part becomes equal to 0. So alpha I di equal to 0 when you differentiate as per the Lagrange condition 2. Okay. Now, in order to find alpha, we cannot find alpha using this one, because everything in terms of this one, this was a primal problem. We have to convert into the dual problem. So we'll see that what is that particular dual problem. So at the saddle point means stationary point, each Lagrange multiplier alpha, the product of the multiplier with its corresponding constant values vanishes, and you are shown by something like this if that particular value comes out to be. Only those multiplier exactly meeting above equation can assume non-zero values, otherwise not. So the primal problem deals with convex cost function and linear constraints that we have seen. Now, given such constraint problem, it is possible to construct another problem called the dual problem. So remember that I was saying that so solution can be found so either primal, solving at the primal, or the dual. And in this case, we have only found this variable w and b. That also we have found a relation, not the exit solution. Now we have to find the value of alpha, because your w and b is always in terms of alpha here, but we don't know what is the alpha. So for that we have to transform this problem into the dual problem. So we'll see that how do we do that. So dual problem has the same optimal values as the primal as per the theory we discussed last class, but with Lagrange multipliers providing the optimal solution. In a dual, the Lagrange multiplier will give the solution rather than the basic variables. So duality theorem here something goes. So it says that if the primal problem has an optimal solution, the dual problem also has an optimal solution, and the corresponding optimal values are equal most of the time. Now, in order for WO to be an optimal primal solution and alpha O to be an optimal dual solution, it is necessary and sufficient that WO is feasible for the primal problem, and this condition holds. That is phi of j, this one. We minimize W based on this one, right? This is obvious, which we did this one. We started with this particular thing. Now we are going to postulate the dual problem for the primal, and we have to be very careful. So I write it down, so and I'll do it in bold so that it will be clear from where I'm writing this. So let me just
Excuse me, sir.
Yeah.
So can you please check the chat? Actually, Nikesh's mic isn't working. He had it out.
Okay, okay. Just a minute. Just a minute. Uh, Explain how we got the joint constraint and why do we have it greater than 1. Yes. Okay. So here we go. This was there. This was clear. This is initially we started with. So we are saying this instead of equating with 0. So why can't we write something like this? It is not going to lose anything. As a result, what is giving this particular distance earlier we are in this, what we are doing, we are referencing to this origin point. But actually we have to talk about from +1 -1 means positive class and negative class. What is that particular value? So some distance should be there. For that we have considered here this particular thing as a +1 and -1 from either side, right? So when I have, so this, I think from this to this, whether it is clear? Any one of you, can we just tell me whether from this to this, is it clear? Hello? Bolo bhai. So I assume that it is clear. This is straightforward. The same thing I've written there. Now instead of writing two constants, I'm just clubbing this. When I club this, how do I club this? So when I rewrite the equation in this particular format, and then in this particular thing, and forget about this for the timing, and you forget about this also. Now when I say that for di when di equal to plus 1, you substitute in this. What will happen? It will remain w naught t xi plus bi. So this is greater than plus 1. Now when di equal to minus 1. So when you apply minus 1 and you multiply to this, so instead of reflecting this minus here, basically what happens, this inequality sign changes, and this minus 1 definitely will multiply here. So when you multiply this side, it is reflecting in the inequality sign, and when the right side becomes minus 1. So this is nothing but your second constant, and that's why I'm saying that instead of writing two constant, we can put it across this one. So Nikesh, say something, yes or no? Okay, fine. So, and make sure that your this mic works here. What do you do with the mic? That it is always not working. Take care of it. Now, if this is the case, so let me go to the board again because a lot of board work is required. So I'll just put it across here. So actually we have to derive this or reduce that dual. So let me write this B alpha. We set this 1 by 2 WT W minus I equal to 1 to N and alpha I di WT xi plus B minus 1, right? And we saw when you take this 0, so this gave, hello, yeah, hello, anybody? So this gives us W equal to summation I equal to 1 to N, right? And alpha I di xi and other constant dj b equal to 0. This condition gave us I equal to 1 to N alpha I di equal to 0. Now what I'm trying to do this, I'm going to rewrite this in such a fashion. I want to derive the dual problem from this. But before that, let me expand this. When I expand this, so I can write now J W B alpha equal to 1 by 2 W2 as it is minus I equal to 1 to N alpha I. I'm just going only inside this. So alpha I, and we can say di WT xi, right, minus, because this one is also there. So I equal to 1 to N alpha I di b, right, b, and plus, because this is minus and this minus plus, I equal to 1 to N, and you have summation alpha I. That's all, alpha I, right? Now if you see this one, this particular part, we can first of all, what is this alpha I di we saw from this one? It is nothing but equal to 0, which we got it after substituting this result from the primal. We got this, right? This part is 0. So if you take b is anyway, it's without any index, so I can take b common out, and this part is 0, so overall thing is 0. Now this, we know that alpha I di xi is something of this form, right? This form. So can I write something like this? 1 by 2 WT W minus Hello. So this is something like, or before that, I write up like this. Let's see that what is going to be this value. Actually, W2 is there. So this alpha dixi is nothing but a W itself. So, but before that, let's try to understand this. How much this W comes out to be. So W is nothing but WT is nothing but I equal to 1 to n alpha I di Wt xi only. When you substitute for this Wt also, so because transpose we cannot write in this fashion, so I have to put one more summation, something like this itself. So I equal to 1 to n, I can say j equal to 1 to n. Here I'll write alpha I, alpha I, alpha j di dj xit xj, because these are the scalar things, so no problem. Here these x are the vectors, so I have to write over there. Now when I do this, so ultimately what I'm trying to say, this entire part is nothing but WTW only. So further I can write that JWB alpha is nothing but 1 by 2 WTW minus WTW plus this this part I equal to 1 to n alpha I, whatever. Now half minus 1, half minus 1, so this becomes basically, so I can write this in this particular fashion. I equal to 1 to n alpha I minus half W2W. So instead of writing like this, so basically this gives us the another objective function we are calling as a Q, and which is everywhere now is function of alpha. How it's going to be I equal to 1 to n alpha I minus 1 by 2, this entire part I equal to 1 to n, j equal to 1 to n alpha I alpha j di dj xit xj. See, this entire formula is in terms of alpha. So this is our dual problem, dual objective function. So this is, now I'll quickly go through. Already have talked about this. So this we have already done it now. When substituting for this, we get something like this. Now the question comes, so what? So what if we found this one? What's the big deal? So there is no big deal as such. We have started from primal, and from primal two constraints are there, and from those two constraints we could find expression for W and expression for B. But exact relation we could not get, because that is still in terms of Lagrange multiplier. So we want something independent of Lagrange multiplier. For that we have to solve the dual problem, that is this one. So we'll try to reframe an optimization problem for the dual. So the statement of dual problem is, or the dual problem is something like this. Given the training this and this, find a Lagrange multiplier that maximizes the objective function. Remember that in the primal we had to minimize the objective function. Here, so dual will be always opposite of that. The nature of that will be opposite. If the primal was minimization, so dual will be the maximization. So we have to maximize. Subject to the constraint that this we got it from primal, so we have to assume that this is equal to 0. And this, of course, alpha has to be greater than 0. So this we have to constrain. So these are the things, and we wrote this one. So to be maximized depends only on the input patterns in the form of set of dot products here. Xi and Xj, those things are there, right? So if you see here, only Xi and Xj are there, dot products we required. So for this one, there is a, now suppose you have found this. Let's say you have found this. So having determined Lagrange multiplier alpha, from where you will get it? Straight away, we can take this dou q by dou alpha equate to 0, and you'll be able to find the expression for alpha, of course, subjected to this particular constraint. Once we have this, suppose we have found this alphas, and I'm calling alpha optimal I bigger because there are many alphas. So by substituting this in the original equation for the WO which you got from the primal, so WO equal to 1 to n alpha OI di xi, and once you have this, bias can be found very easily, and you will be able to find this WO, and from this particular relation you can find BO 1 minus WT XS. And remember that XS is nothing but the support with this one vectors. That is a vector when the value comes out to be 1. So this is how you do the primal problem. We'll do one particular problem on this. Particularly we'll try to do this XOR problem at a later point of time. But first of all, make sure that you have really understood from the first principle itself, how we started with, and we found the expression for this primal optimization problem definition. Then from that, we deduced this dual optimization problem definition. Is there any query from any one of you? Please go ahead, ask now. Hello. So if there is no query, I'll move further. Now we'll go for this another point, and what is called optimal hyperplane for non-separable patterns. So this has to be looked into a completely different way. So earlier was basically primal problem separable. This is for the non-separable. Means simply we cannot find this. So they are not linearly separable. So how do I do this? So let's consider the case of non-separable patterns. So that's why initially we developed something, and you'll be getting something surprising result, that there is some sort of one concept is being used in case of dual, even though problem is completely different. The dual problem for both this one linearly separable and non-linearly separable remains same. So we'll see that. So given such a training data means they are non-linearly separable, it is not possible to construct a separating hyperplane without encountering classification error. So, but you want to find an optimal hyperplane such that classification error can be minimized, if not eliminated altogether. So this is what we are going to find out, that minimize the probability of classification error average over the training data. We cannot say that will make this classification error zero. May not be possible. So margin of separation between a class is said to be soft if a data point violates the following condition. It is if violating something this kind of condition which we already seen, it will be margin will be soft here. And these violations can arise in one of two ways. There are two possibilities, and this will show with the diagram also. Data point falls inside the region of separation, but on the right side of decision surface. This I'll explain with the diagram, just hold on. And the data point xi falls on the wrong side of the decision surface. So this is what I mean to say, just hold on for a minute. In this case, suppose all these rectangular boxes, they indicates positive class, and these O's are representing negative class, let's say. So this is the margin of separation from here to here. So what is happening? The first point I was talking about, there could be a problem from what is the cause of violation. This violation xi falls inside the region of separation, but on the right side of the decision surface. When I say right side means within the, anything above this will be classified as a positive class, but actually it should be somewhere here beyond the margin line. But if it is falling here between this particular distance, so there is a violation. But because it is above the optimal hyperplane, it will still be classified properly. Right? Now let's case here. In this case, another one, there is another kind of violation is that here what is happening, data point is falling within the region, but it is beyond the optimal hyperplane. So definitely if it is beyond the optimal hyperplane, so below this only will be labeled as a negative class, but above that it is positive class. So even though the data point belongs to a negative class, it will be classified or labeled as a belonging to positive class. So here in this case, data violation is there also. This kind of data violation will cause classification error here, even though there is a violation as far as SVM is concerned, but it is not causing data misclassification. Okay, so we have the correct classification in the case 1, but misclassification in case 2. Now, for this to measure this, we have to modify our separating hyperplane condition to some extent. We wanted to know, and let me call that this particular point, how far it is deviated from its ideal position. Ideal position is from here to here, what is the distance? From here to here, what is the distance? And this particular thing is measured by a variable called as a slack variable. Slack variable. So let's say this is this distance and this one from this dotted line to this solid line is the 1 from either side. So this way of saying that it is beyond this, so it is deviated, so this should be subtracted. So it is z, xi, z. This particular symbol is called xi, z. So it is like that. And now, so as I mentioned, the z's are called slack variables. They measure the deviation of the data point from the ideal condition of pattern separability. Okay, pattern separability. So, and also this value lies between 0 and 1, obviously, because this entire distance is 1 only. So your z cannot be more than 1. It could be, if anything is lying on this, definitely it is z is 0. If it is beyond this, so z is having some no negative value. And it can be greater than 0, but less than 1. It cannot be more than 1. So the data point falls inside the region of separation, but on the other side of the decision boundary. Instead of saying right side or left side, we'll say other side of the decision surface. If this happens, the z is greater than 1, it falls on the wrong side. So basically, in this case, what happens when this is lying between this on the right side, or we can say that within the side of the decision surface. So what do I mean by this? See, from this to this, the distance is only 1. So if z is lying between 0 and 1, it means it is lying within here only. It means data violation happens, but it will not cause any misclassification error. But if z is beyond 1, it means it goes another side, means more than this particular distance, other one. Distance from here to here, definitely it is more than 1. And in this particular situation, the data violation which is resulting is cause a misclassification error. This is what it says here. Okay. And so the support vector are those data points that satisfies this one in this particular scenario. And even if z is greater than 0, whatever. Now, if an example with z greater than 0 is left out of the training set, if you remove it, a decision surface would change, because if that is the case and which has not been part of training, so definitely your whatever decision surface you are taking care of, it may not completely characterize the characteristic of the, or it will not capture the characteristic of the data which you are studying. Now support vectors are defined in exactly the same way for both linearly separable and non-separable case. So our goal is to find a separating hyperplane for which the misclassification error averaged on the training set is minimized. That's what we are looking for. So we'll see that. So for that, we in order to count for it, so we use the concept of something called functional. We wanted to just know this. We want to count how many errors are there. So this is something called, in machine learning we also call as something called indicator function, as simple as that. So whatever is mentioned here, so I'll tell you something like this, the concept of indicator function. So it's like an indicator function. So if I say I and whatever is there, if the value is, I'm saying that 2 is equal to 5 minus 3. So if it is true, whatever the condition here, then value will be 0, and if it violates, if it violates, the value will be 1. So I can say condition, whatever the condition is, or let me put very simply, the condition, whatever the condition may be, this equal to 1 if the condition is I think I'm saying ulta. Condition is true. Yeah, it's true, and 0 if the condition is false. So what I mean to say here, suppose if you write here sometime indicator function, instead of writing I, people write just 1, and I say that 3 is greater than 2. So what value comes out to be? The value, of course, 3 is greater than 2. It should be 1. The value is 1. This is the case. Likewise, here you are saying that in this case, we had this particular case. We wanted to know. So instead of writing like this also, we just wanted to know, we wanted to count the number of errors. If we want to count the number of errors, so I can just find it out that I equal to 1 to say n 1, and I'm saying that 1 greater than 1, let's say. So you count that out of 1 to n example, for how many data points that deviation is greater than 1. Whichever is 1, this will count 1 for that particular. It will be a flag. And how many such flags are there? One thing is, we already decided and agreed that whenever this will be there, the violation, the data point violation, will cause a misclassification error. So this will give you misclassification error effectively. Now instead of writing like this, which is most popular or the convention in machine learning, in this what Simon has done is he has written in this also more intuitive ways, another way of doing it. So saying z minus 1, so definitely it means z is greater than 1. So whichever is happening, you count those many number of points, and that will give you the basically the errors. So then we want to minimize the functional, means we want to minimize this particular error subjected to separating surface condition constrained on W. So this I have already defined it. If it is greater than 0, means that is going to be true. So this will be 1, otherwise it's 0. Means if it is less than, so it is not causing any misclassification error, so it will be 0 only. If it is greater than 1, so this is indicating that there is an error. This is what it means to say. So here if I write z greater than 1, even that is also fine. Minimization of phi z with respect to W is a non-convex optimization problem, that is NP complete, and you cannot find it out. So it's and convex because we cannot just differentiate this. So we have to write this in some other fashion. So we simplify the computation by formulating the functional to be minimized with respect to this one. This is of course is the basically binom square, and this we are, instead of trying indicator, we are putting something like this. We basically control error upper bounds on the number of test error. How many errors are there is giving upper bound. Now parameter C basically controls the trade-off between the complexity of machine and the number of non-separating points. Also, this functional phi WZ is optimized with respect to W, and this subjected to the constraint of separating hyperplane. And we'll see this is how we state this. So we say that now the primal problem is something like this. The training samples find the optimal values of weight vector W and bias B such that they satisfy the constraint this one. Remember that these are the constraint for the primal definition for the primal problem. So something like this, and we saw that Z could be greater than or equal to 0 for all I, and such that weight vector and the slack variable Z minimizes this cost function. So this we have to minimize this. Remember, this cost function is in terms of the number of errors. So where C is a user specified parameters. So for this process, so I'm not going to follow the same process, but it is the same process what we have done. We have to do the write this for the first from this we have to write the Lagrange function. From the Lagrange function, you find the two constraints, and depending on how many sets of constraints, two sets of constraints are there, one for this one, another for this one. Two set of Lagrange multiplier will be used. Either you can use alpha and beta, and then you differentiate with respect to w and z and equate to 0. Those two constraints will be there. So formally we represent whatever we have mentioned on the previous slide can be represented something like this. We have to minimize this subjected to these particular conditions. And now, as I said, we follow this Lagrange multiplier, and then we use this again on top of this one. That is, we go for the dual formulation, and dual formulation is something like this. So the same process, whatever we have done earlier, this is extended to this. So I'm not doing this again. So from this dual formalization, we get this particular equation, and you'll be surprised to see that even though primal problem is quite different, they are pole apart as compared to the linear separation condition and the non-linear separation condition. The dual optimization variable of the objective function remains same in either the case. This is quite surprising. But and this constraint will be there, and of course this alpha is now upper bounded by C. You cannot have anything else than C. So once we solve this, we can get this number. Also, as I mentioned this, neither the slack variable nor the Lagrange multipliers appear in the dual problem. That is surprising. Here, so many things we are no, we are getting only one Lagrange multiplier, not all. So, but nowhere slack variable is appearing in the dual problem. Dual problem for the case of non-separable is similar to that of the linearly separable case. And in this case, once we find the optimal solution, so WO, so alpha DIX, depending on the how many support vectors are there, and for B, we can find something like this. Now with this, we'll try to, so I'll stop here today's class. And in the next class, I'll talk about this, how do I apply, we'll take one particular problem and solve it manually, that this is how can be applied to. Particularly, we'll take this SVM case and we say, XOR problem is a nonlinear classification problem, and we'll try to apply SVM and see how it can be solved. Also, we'll see this before that, how can I make it introduce the concept of kernel, which is more generic in nature. By changing the kernel, you can capture a lot many things. So those ideas will take it up in the next class. Okay. So we'll stop here. Just be there.